All charges, whether free or bound, were considered to be at rest. Charges in motion constitute an electric current. Such currents occur naturally in many situations. Lightning is one such phenomenon in which charges flow from the clouds to the earth through the atmosphere, sometimes with disastrous results. The flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in a steady manner, like water flowing smoothly in a river. Electric current. If we want to find out the current flowing through a conductor BC, then we should connect the ammeter A in series with the conductor BC. Since the entire current passes through the ammeter, therefore an ammeter should have very low resistance so that it may not change the value of the current flowing in the circuit. Imagine a small area held normal to the direction of flow of charges. Both the positive and the negative charges may flow forward and backward across the area. In a given time interval t, let Q positive be the net amount of positive charge that flows in the forward direction across the area. Similarly, let Q negative be the net amount of negative charge flowing across the area in the forward direction. The net amount of charge flowing across the area in the forward direction in the time interval t then is Q is equal to Q positive minus Q negative. Electric currents in conductors. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charged particles do exist, like in upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules, a gram of water. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the negatively charged electrons carry the current. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. In our discussions, we will focus only on solid conductors so that the negatively charged electrons in the background or fixed positive ions carry the current. Ohm's law.
When key is pressed, current flows through the circuit. As a result, deflection takes place in ammeter and voltmeter. According to Ohm's law, ratio of potential difference between the ends of the conductor to the current flowing through it is a constant, and this constant is known as resistance.
Imagine a conductor through which a current I is flowing, and let V be the potential difference between the ends of the conductor.
According to Ohm's law, ratio of potential difference between the ends of the conductor to the current flowing through it is a constant. Hence, a graph of V versus L is a straight line passing through the origin.
Then, Ohm's law states that V is proportional to I, or V is equal to Ri, where the constant of proportionality R is called the resistance of the conductor. The SI units of resistance are ohm and are denoted by the symbol ohm. The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor, drift of electrons, and the origin of resistivity. In this animation, the full lines shows that the electron moving from a point A to another point B through repeated collision and straight line travel between collisions. The dotted line shows if an electric field is applied, the electron ends up at point. A slight drift in a direction opposite the electric field is visible. An electron will suffer collisions with the heavy fixed ions, but after collision, it will emerge with the same speed but in random directions. Mobility. As we have seen, conductivity arises from mobile charge carriers. In metals, these mobile charge carriers are electrons. In an ionized gas, they are electrons and positive charged ions in an electrolyte, and these can be both positive and negative ions. Resistivity of various materials. The materials are classified as conductors, semiconductors, and insulators depending on their resistivities. In an increasing order of their values, metals have low resistivities in the range of 10 to the power minus 8 ohm m to 10 to the power minus 6 ohm m. At the other end are insulators like ceramic, rubber, and plastics having resistivities 10 to the power 18 times greater than metals or more. In between, the two are the semiconductors. These, however, have resistivities characteristically decreasing with a rise in temperature. The resistivities of semiconductors are also affected by presence of small amount of impurities. This last feature is exploited in use of semiconductors for electronic devices. Temperature dependence of resistivity. The resistivity of a material is found to be dependent on the temperature. Different materials do not exhibit the same dependence on temperatures. Electrical energy, power. Consider a conductor with end points A and B in which a current I is flowing from A to B. The electric potential at A and B are denoted by V to A and V into B respectively. Since current is flowing from A to B, V into A is greater than V into B, and the potential difference across AB is V is equal to V into A minus V into B is greater than 0. Combination of resistors to series and parallel. Of resistances. When two or more resistors are connected end to end consecutively, they are said to be connected in series. Two resistances R1 and R2 which are connected in series. When two or more resistances are connected between the same 2 points, they are said to be connected in parallel. The two resistances R1 and R2 are connected in parallel arrangement between the same 2 points A and B. The current through a single resistor R, across which there is a potential difference V, is given by Ohm's law I is equal to V by R. Resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combination of two resistors connected in series.
Two resistances R1 and R2 connected in series. A battery of V volts has been applied to the ends of this series combination. The potential difference across the resistance R1 is V1 and R2 is V2. We have applied a battery of voltage V. The two resistances should be equal to the voltage of the battery. That is, V is equal to V1 plus V2, equation 1. Suppose the total resistance of the combination be R and the current flowing through the whole circuit be I. Applying Ohm's law to the whole circuit, V upon I is equal to R or V is equal to I into R, equation 2. Since the same current I flows through both the resistances R1 and R2 connected in series, V1 is equal to I into R1, equation 3, and V2 is equal to I into R2, equation 4. Putting the values of V, V1 and V2, we get I into R is equal to I into R1 plus I into R2, or I into R is equal to I into R1 plus R2. Resultant resistance, that is combined resistances or equivalent resistance, R is equal to R1 plus R2.
Two resistors are said to be in series if only one of their end points is joined. If a third resistor is joined with the series combination of the two, then all three are said to be in series. Combined resistance of two resistances connected in parallel. Two resistances R1 and R2 are connected parallel to one another between the same 2 points A and B. A battery of V volts has been applied across the ends of this combination. The total current flowing in the circuit is I. Then the current passing through resistance R1 will be I1. It is obvious that total current I is equal to I1 plus I2. Suppose the resultant resistance of this parallel combination is R. We get I is equal to V by R. Since the potential difference V across both the resistances R1 and R2 in parallel is the same. So, by applying Ohm's law to each resistance separately, we get I1 is equal to V by R1 and I2 is equal to V by R2. Now putting the values of I1 and I2, we get V by R is equal to V by R1 plus V by R2, or V into 1 by R is equal to V into 1 by R1 plus 1 by R2. 1 by R is equal to 1 by R1 plus 1 by R2. If two resistances R1 and R2 are connected in parallel, then their resultant resistance R is 1 by R is equal to 1 by R1 plus 1 by R2. Two or more resistors are said to be in parallel if one end of all the resistors is joined together and similarly the other ends joined together. Cells, EMF, internal resistance. A cell has two electrodes called the positive P and the negative N. They are immersed in an electrolytic solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. Cells in series and in parallel. In series and parallel. Consider the first two cells in series where one terminal of the two cells is joined together, leaving the other terminal is either cell-free. E1 and E2 are the EMFs of the two cells and R1, R2 their internal resistances. Two cells of EMFs E1 and E2 in the series R1, R2 are their internal resistances. For connection across A and C, the combination can be considered as one cell of EMF E suffix EQ and an internal resistance R suffix EQ. Therefore, E suffix EQ is equal to E1 plus E2 and R suffix EQ is equal to R1 plus R2. Consider the two cells in parallel for connections across A and C. The combination can be replaced by one cell of EMF E suffix EQ and internal resistance R suffix EQ, whose values are given in E suffix EQ is equal to E1 R2 plus E2 R1 by R1 plus R2. R suffix EQ is equal to R1 R2 by R1 plus R2. Like resistors, cells can be combined together in an electric circuit, and like resistors, one can, for calculating currents and voltage in a circuit, replace a combination of cells by an equivalent cell. Kirchhoff's rule. Electric circuits generally consist of a number of resistors and cells interconnected, sometimes in a complicated way. The formulae we have derived earlier for series and parallel combinations of resistors are not always sufficient to determine all the currents and potential differences in the circuit. Two rules called Kirchhoff's rules are very useful for analysis of electric circuits. Wheatstone Bridge. Wheatstone Bridge. Wheatstone Bridge is working in the application of the Kirchhoff's rules. We assume that the cell has no internal resistance. Thus, there will be the current flowing across all the resistors as well as a current Ig through G. In the case of balanced bridge, where the resistors are such that Ig is equal to 0, in this case, the Kirchhoff's junction rule applied to junction D and B immediately gives us the relations I1 is equal to I3 and I2 is equal to I4. The first loop gives minus I1R1 plus 0 plus I2R2 is equal to 0 as equation 1, and second loop gives using I3 is equal to I1 and I4 is equal to I2. I2R4 plus 0 minus I1R3 is equal to 0 is equation 2. From equation 1, I1 by I2 is equal to R1 by R2. From equation 2, I1 by I2 is equal to R4 by R3s. Hence, we get R2 by R1 is equal to R4 by R3. This balance condition of the Wheatstone bridge is provided a practical method for determination of an unknown resistance. Wheatstone bridge has 4 resistors R1, R2, R3 and R4. Across one pair of diagonally opposite points, a source is connected. This is called the battery arm. Between the other two vertices, B and D, a galvanometer G is connected. BD is called the galvanometer arm. Meter bridge. Meter bridge. We have to use the meter bridge to determine the unknown resistance R. These unknown resistance connected across the one of the gaps, across the other gap, we connect the standard known resistance S. The jockey is connected to some point D on the wire a distance L centimeter from the end. Let the distance of the jockey from the end A at the balance point B L is equal to L1. The 4 resistance of the bridge at the balance points are R, S, R centimeter L1 and R centimeter 100 minus L1. Thus, the balance condition R by S is equal to R centimeter L1 by R centimeter 100 minus L1 is equal to L1 by 100 minus L1. Thus, found out L1, the unknown resistance R, is known in terms of standard known resistance S by R is equal to S L1 by 100 minus L1. The meter bridge consists of a wire of length 1 meter and of uniform cross-sectional area stretched taut and clamped between 2 thick metallic strips bent at right angles as shown. The metallic strip has 2 gaps across which resistors can be connected. The end points where the wire is clamped are connected to a cell through a key. One end of a galvanometer is connected to the metallic strip midway between the two gaps. The other end of the galvanometer is connected to a jockey. The jockey is essentially a metallic rod whose one end has a knife edge which can slide over the wire to make electrical connection. Potentiometer. This is a versatile instrument. It is basically a long piece of uniform wire, sometimes a few meters in length, across which a standard cell is connected. In actual design, the wire is sometimes cut in several pieces placed side by side and connected at the ends by thick metal strip. The wires run from A to C. The small vertical portions are the thick metal strips connecting the various sections of the wire.